So, so before we go to the bounds on the minimum distance and all that, I promised I will show you something about d equals 4, I forgot about that. So, let us come back to that real quick. Okay. So, you can see what modification will be most useful when you want to go to d equals 4. We know how to do d equals 3. How do you go from d equals 3 to d equals 4? Extension, and that turns out to be quite good in most scenarios. Okay. So, basic idea for d equals 4 is you do d equals 3, design d equals 3, and then you do an extension to go to d equals 4. Okay. So, I will illustrate it only for the 7-4 Hamming code just to see that it works, and then we will leave it at that. Okay. So, simple example. So, let us start with the 743 Hamming code. Okay. So, you have a parity check matrix which is maybe I will write it in systematic form, so that okay. So, some of you might complain, I said the 7-4 Hamming code had some other kind of parity check matrix, but that and this parity check matrix are quite equivalent. What is the only thing I have done? I swapped columns, and we do not mind the swapping of columns. Okay. It is all equivalent, so we do not mind that. So, this is the 7-4 Hamming code. What will happen if I extend it? Okay, I am going to get a 8-4-4 code. Okay. So, this is a very interesting code, it is a very well studied code, but we may not see all those properties, but I will simply write down what the extension will look like. So, okay, so idea behind an extension is I am adding an overall parity check, and basic thing is to simply add 1 and then put a 0 here. Okay. So, that would be the parity check matrix of the extended version. Okay. So, here you can clearly see in this code C8 is what? C8 is the XOR of C1 through C7. How do I quickly see that? Just look at the last parity check. Okay, so, that basically says C1 plus C2 plus C3 plus so on till C8 equals 0. So, I can write C8 as C1 plus C2 plus C3 plus C7. Okay. So, that is something that you can do. Alright. So, this is the extended bit. Okay. And C1 through C7 clearly satisfy the original parity check matrix, and that is the 7-4 Hamming code. So, this is the extended version, and you get 8-4-4. Okay. So, anytime you want to design a d equals 4 code, this is what you would do. You try to design a d equals 3 code with comparable parameters, and then extend and you get d equals 4. Okay. So, this is pretty good. Okay. So, that is one comment I wanted to make before we move on. Okay. So, here is another quick comment which I want to get rid of before we proceed further. Okay. So, this has got to do with positions of message bit. Okay. Position for message bits. Okay. So far we have been looking at systematic form for the generator matrix, which is of this form IP. Okay. So, we always think of a code word as having a message first and then having a parity. Okay. So, if you take an example, maybe if I take the previous example or any other example, okay, I could have a G which looks like this, let us say 100, 010, 001, let us say 110, 011, 101, something, I mean any example you can take. So, when you stare at it, you think of the message as occurring in the first 3 positions, and the next 3 positions is a code word. Okay. So, there are various interpretations which you have to be careful about. For instance, if I say XOR the second and third row, okay, suppose if I XOR the second and third row, what do I get? I will definitely get an equivalent generator matrix. Okay. And how would that look? 0 1 1 1 1 0, am I right? Do I want that? Okay, so the last row is going to remain the same. Okay. So, now if you look at it, it looks like, I mean, where is the I gone? The last column of I has gone to the last position. Okay. So, these 2 guys are remaining the same, and then the last column has also become. So, these 3 columns together will complete the identity matrix. So, now I can say in this version, the first, second and 6th bit are my message bits, and 3rd, 4th and 5th are parity bits. Okay. So, what I want to point out, it is just a brief point, it is not a major thing, but the positions of the message bits can be anywhere on in the code word. Okay. So, depending on row manipulations, you can get it to be anywhere. Okay. Not necessarily in the first 3, first 3 is a convenient thing to keep for various implementation purposes and all that, but otherwise it does not really matter, it can be anywhere. Okay. What is the condition on say some k columns? Suppose I pick any k columns of the generator matrix, when will those k columns be capable of being message bits? What is the condition? Yeah, linearly independent is what is important. Okay, yeah, of course, after row elimination I should be able to create a identity matrix there, which means originally those k columns must have been linearly independent. Okay. As long as you have k columns of G which are linearly independent, those can possibly be message bit positions. Okay. Now, if you go to the parity check matrix, you will have a similar situation, but there it is a little bit more subtle. If you look at the parity check matrix, okay, so you usually think of it as P transpose I n minus k. So, here also I can do row manipulations, okay, and then move my I wherever I want, but what does the position of I indicate in the parity check matrix? Is it the message bits or the parity bits? It is a parity bits, so that is the difference. Okay. So, once again I can pick any n minus k columns in H and ask when will those n minus k columns correspond to parity bits, when will that be possible? When they are linearly independent. Okay. So, that's a small point I wanted to make, which you should be familiar with. Okay. So, you will see a lot of people trying to move their message bits around here and there, it does not matter where they are. Okay. As long as those columns are linearly independent, you can either assign them to message in the generator matrix or parity in the parity check matrix. Okay. So, that is the idea. Okay. So, this IP and P transpose I is just a convenient form, the columns of I can be interspersed all over the matrix. Okay. All right. So, let us just do away with that and then move over to bounds. Okay. So, I will do them reasonably quickly. It is good to know a few bounds, so that we have a feel for what happens with these parameters n, k and d. Okay. So, the first bound we will see, yes. Yes.
The message bits may be contained in a set of linearly independent columns, but may not be apparent as such. In the sense, unless you get linear columns which in some form can be written swapped such that they form identity matrix, you may not get the message bits as such from those.
I think I understand your question. So, you are saying in a given form of G, you may not have the I occurring in a set of linearly independent columns. Yeah, you will have to do some row manipulation to get the I there if you want those to exactly correspond to your message. Okay. But those k bits will be in 1-to-1 correspondence with your message. You can always go from one to the other. They may not exactly match your message bits, but there will be an invertible matrix which will multiply your message bits to give you that. Okay, so let us see the first bound, which is called the Hamming bound. Okay, so this is a useful bound to have. Okay, so here a picture is very nice to illustrate what the Hamming bound does. It is also called the sphere packing bound. You will see how why that is called so. Okay, so our bounds will be for NKD codes. Okay, so I will start with an NKD code and try and establish some bound between relating K, N and D. What do I mean by bound? Some inequality. Okay, so I will come up with some inequality which relates N, K and D, okay, and that will end up being a bound on one or the other. Okay, so let us say this is F2N, okay, and let us say I have marked out all my code words. Okay, I have marked out all my code words. Okay, so now what I am going to do is I am going to draw spheres or circles around each of my code words. Okay, and what does that circle include? Okay, it will have say radius what? I will use radius some t. Okay, so some small t radius. So what do I mean by radius? Now I have to be careful. My distance is not some Euclidean distance. It is going to be Hamming distance. Okay, so let us say we will pick one guy and draw a sphere or radius of circle or circle. I am sorry, a circle of radius t. Okay, let us say a sphere of radius t. Okay, it is called a Hamming sphere because it is in Hamming distance. Okay. So my first question is, suppose I do it for some radius t, how many vectors will be inside this sphere? Okay. Okay, so we will think a little bit about this. Okay, so what is the question I am asking? I am giving you an arbitrary vector and then I am asking how many vectors are a distance at most t away from that code word. Okay, yeah, so I have to add up everything. So what will happen is, first I have the code word itself. Okay, I have the code word itself and then I have set of all vectors which are a distance 1 away from my code word. How many vectors will there be? How do I think of this? So I have one vector, I want all vectors that differ from this code word in only one position. In how many ways can I pick that position? N choose 1. Okay, so I will get N choose 1 vectors which are a distance 1 away from my code word, chosen code word. Then I will have N choose 2 code words vectors which are away in 2 positions. Okay, so on I can add up and go all the way to N choose t. Okay, so that is the first idea. Okay. Okay, so there are a lot of ideas here about Hamming distance that will come out in this bound. Okay, so hopefully all this is useful also. Is it clear? Hopefully you are able to visualize what is happening. I have one vector and then I see all vectors which differ in this in only one position. Okay, that I can have n of them and then I choose N choose 2, I pick 2 positions and I flip those bits, I will get another vector. Okay, so N choose 2, N choose 3, so on till N choose 3. Okay, that many vectors you have in a Hamming sphere of radius t around each code word. Okay. Now I want to draw such spheres around all the code words and still not have them overlap. Okay, what is the maximum possible t that I can pick? That is the question. Okay. Okay. Okay, so suppose let us say there is one code word here and there is another code word here which is exactly a distance d away. Okay, maybe those two form a minimum code word pair. Okay, there will be 2 such things, right, because I have an NKD code. So there will be clearly 2 code words which are separated by exactly d positions. Okay. Now if I draw another guy of radius t here, okay, when can I be absolutely sure that they will not overlap? Okay, if 2t is less than d, right, if 2t is less than d, then I can be definitely sure. So now you are using some Euclidean insights. Remember I am dealing with Hamming distance. How do I know that such an inequality holds in Hamming distance, right? So you have to check that. It's easy to prove that also. So Hamming distance will obey a triangle inequality kind of thing. Okay, so if you have 2 things a distance d apart, you start at one and you flip t, you start at the other and flip another t arbitrarily, these 2 will not be meeting if 2t is less than d. okay. So that requires some explicit proof, you can write it down, it is not very difficult, okay. So I can pick such that t such that 2t is less than d, okay. So there is another way of writing this down. What is the largest possible t which will have 2t less than d? You have to do floor of d by 2, okay. So floor of d by 2 is a little bit dangerous. Why? If d is even, you will have a problem. So what, how can you avoid that? D minus 1 by 2 is just absolutely safe, okay. So nothing will happen to you. So you pick a t like d minus 1 by 2, okay. So for instance you might want to pick t equals d minus 1 by 2, say you can floor this, okay. So then there will be no problem, okay. So you will definitely get valid thing, okay. So what is the next step now? Now I have drawn these spheres around each of these code words, and I know none of these spheres overlap with each other. What do I mean by overlap? There is no vector in each of these spheres which is common to 2, okay. There is no vector here which is common to more than 1, okay. So that is the idea, okay. So now I have a bound, okay. How will I do a bound now? Think about it, okay. Yeah. So if you now multiply this number of vectors in each sphere by 2 power k, why am I multiplying by 2 power k? I have 2 power k code words. So I have 2 power k such spheres. Now I am counting the total number of vectors inside the Hamming spheres of radius t. So that will be 2 power k times this, okay. Now I know I did not overcount because none of the spheres have any overlap. So clearly this 2 power k times this should be less than the total number of possible vectors in the entire space, which is 2 power n, okay. So that is the sphere packing or Hamming bound, okay. So 2 power k times 1 plus n choose 1 plus n choose 2 plus so on till n choose d minus 1 by 2 floored okay. So let me draw this down a bit more clearly, is less than or equal to 2 power n, okay. So that's an inequality which relates n, k and d, and it's valid always. Any n, k, d code you have, this has to be satisfied. You cannot violate this. N, k, d binary code will satisfy this condition, okay. So codes that meet the Hamming bound. What do I mean by meeting the Hamming bound? This inequality is actually a equality. That's when something meets an inequality, okay. So if it meets this bound, then those codes are called perfect, okay. So there is a reason why they are called perfect, we will see them later on, but those are called perfect. And there is a very surprising statement about perfect codes. People have characterized all possible perfect codes and they are very few in number, okay. Not too many of them, very few codes. You can imagine it is a significant combinatorial achievement to characterize all perfect codes. It is not at all obvious how you would do it, okay. First of all, can you give me an example of a perfect code? Well, Hamming codes are perfect codes, okay. So you can check that, okay. For instance, if you put k equals 3, k equals 4, d equals 3 and n equals 7, you will see that it will meet this bound, okay, and the Hamming code meets this bound. All Hamming codes meet the Hamming bound, okay. So you can imagine the name matches, right. So it has to be true, okay. Okay, so let us see perfect codes meet Hamming bound. Okay, so there are examples, the 2 power r minus 1, 2 power r minus 1 comma 3 Hamming codes. Okay. So I will try and ask you a question about another example. There is another code which is called the repetition code. Okay, I have not introduced this formally, but maybe this is a good time to introduce it. Okay. The parameters are basically n comma 1 comma n. Okay. So I will ask you a challenging question. I give you the parameters of a code, you have to now tell me what the code is. Okay, having code, you know how to do it. So I am telling you there is a repetition code, its parameters are n comma 1 comma n. Okay, what will be the code? See, first of all, n is the number of bits. Okay. K is 1, which means there are only 2 code words. Okay, if you have 2 code words, one of them you already know. What is one code word? It's always there. All 0. There's only one other code word, and what is the minimum distance? N. So what should that other code word be? All ones. That's why it's called the repetition code. Okay, so this is the repetition code, and this code basically, if you call it Cn, is basically all zeros and all ones. You can see why it's called the repetition code. There's only one message bit, which is either 0 or 1. If it is 0, you transmit all zeros, you repeat 0 n times. Okay, that's why it's called repetition code. Okay, if the message bit is 1, you repeat 1 n times. It's called the repetition code, obviously. Is this a perfect code? That's my question.
If n is odd, then either that or this.
N is odd, it is perfect. If n is even, it's not perfect.
If n is even, it's not perfect. Is that correct? Okay, it could be correct. I'm not saying it's not correct. It could be correct. Okay, so for n odd, it is perfect, right? Is it okay? People are clear on it. You can put it into that formula. You will get the answer, I think. Okay, so for n odd, it's perfect. Okay, so it's okay. So that's something you can check. Okay, so if n is even, there will be like this one overlap which will kill you. You know, I mean, this one problem which will not give you. It will be almost perfect. It will not quite be perfect. Okay, another example which I am going to write down is going to be the dual of the repetition code. Okay. Alright, so this is a good test of whether you understood dual or not. Okay, so what will be the dual of a repetition code? First of all, what are the parameters for the dual of a repetition code? N remains the same, and then n minus 1, that's also easy. Now you have to characterize the dual and tell me what will be the minimum distance. What's the easiest way to do this? It's not too difficult. See, you have to come up with the generator matrix for Cn. What will that be for Cn perp, the dual? It will be the parity check matrix, right? So that's the easiest way to go about doing this. Okay, if I have the generator matrix, what's the generator matrix for the Cn? This is the only generator matrix for the repetition code, right? So if I now think of Cn perp, what will be the parity check matrix? Okay, now answer the question, what's the minimum distance? You are not using the definition carefully. When will you have minimum distance? 1? If there is an all 0 column. Is there an all 0 column here? No. When will you have minimum distance? 2. If you have a repetition, do you have a repetition here? Yes. So clearly minimum distance will be 2. Okay. This is Cn perp. There is a very easy way to characterize Cn perp. Okay, how will you describe it in words? Yeah, has to be. Well, yeah, so it's what is called, say, the even parity code or the even weight code. Okay, the code contains all the even weight vectors in F2n. Okay, Cn perp contains all even weight vectors in F2n. Okay, I mean, first of all, it has to contain clearly the all the even weight vectors only, right? How do I know that Cn perp will contain only even weight vectors? Yeah, the sum has to be 0. The parity check is all ones, right? There's nothing I can do about it. It has to contain only even weight vectors. And how do I know it will contain all of them? Yeah, so that is another way to think about it. There is 2 power n minus 1 code words, there has to be exactly 2 power n minus 1 even weight vectors of length n. Okay, so it has to include everything. Okay, there is no problem, just by looking at this, you know it has to work out. Okay, how will a generator matrix for this look like? It's very easy. You have to split it as P and I, no?
Yeah.
So I will come just here. So it will be just simply I1. So you do I n minus 1 and then all ones. Okay. So when you encode this, what do? You have n minus 1 bits, and the nth bit is what? Parity of all the n minus 1 bits. So that's why it's also called the even parity bit, even parity code. Okay. So it's a very simple code to describe. Nevertheless, it has all these intricacies. Okay. So once again, this won't be perfect. Okay, so if you have even minimum distance, it won't be perfect. Okay, so there will be a problem with the spheres intersecting, so it won't work out. Okay, but anyway, this is a good code to keep in mind. Okay, so another curious thing, which if you do not know about binary vectors, it will be a little bit more interesting here. So notice C and perp, I know it's a linear subspace, right? It's a linear code. Clearly, it's a linear subspace. It contains all even weight vectors. So clearly, what should happen if I add 2 even weight vectors? Should be in the same set. Yes, it should also be a even weight vector. Okay, so that's an interesting relationship which you can independently check for Hamming distance. Okay, so you can show this interesting relationship. The Hamming weight of x plus y, you can show, will be equal to Hamming weight of x plus Hamming weight of y minus 2 times Hamming weight of x star y. Okay, what is this x star y? I have to tell you what x star y is. X star y is basically x1 y1, x2 y2, xn yn. Okay, so the 2 times is critical. Okay, the way to prove it is you write x on the top row, write y below. When you add, what will happen? Whenever there is overlap, 2 1s are disappearing. Okay, so this x star y counts the number of overlaps between x and y in positions where you have a 1. Okay, when you add, both of them go away in the sum. So you have to subtract 2 times weight of the overlap. Okay, so if x and y have both even weight, what will happen to the weight of x plus y? It will again be even. What if x and y are both odd weight? Once again you will get even. Okay, if one is odd, one is even, what will you get? Odd. Right, all these things you can nicely prove using these simple things. Anyway, so I digressed a little bit from our bounds. Anyway, I think it's a good digression. It's a nice thing to know these things about the binary vector space. Okay, all right. So the next bound we are going to do is what's called the Singleton bound. Okay, so it's a very famous bound. Okay, so here is how I am going to prove it. Once again, I have an NKD code C. What I am going to do is I am going to take all the code words of C and write them one below the other. Okay, it's just for convenience, just in the proof. You can also imagine it, but I will write it down just for the sake of completeness. So we have C11, C12, so until let us say C1, C1k minus 1, C1k, so on till C1n. Okay, and then I write C21, C22, so on till C2k minus 1, C2k, C2n. Okay, so imagine that the first k positions are message bits. Okay, so that's another thing I am assuming here. Okay, so and all the way down to C what 2 power k1, 2 power k2, C 2 power k minus 1, C 2 power k all the way to C 2 power k n. Okay, so these are all the 2 power k code words that you have in this. Is that okay? You have in this code C. Okay. So once again I told you the first k positions are systematic as in as are message bits. Okay, so the message bit positions are also called systematic positions. Okay, so that's a term that is used all the time. I think I don't know where it came from. It's called systematic bits for some reason. It's a weird reason. Okay, so the first k positions are message bits. What does it mean to say the first k positions are message bits? All the 2 power k possibilities will occur in the first k positions, right? That is what it really means. If I list it down one below the other, it means the first k positions all the 2 power k possibilities will occur. That is when it becomes a message bit, okay, right, because the first k can be message and then every possibility will occur there. Okay. Now suppose I look at the first k minus 1 positions. Okay, so there is a good reason why I wrote k minus 1. Suppose I only look at these guys. Okay, first k minus 1 positions. Okay, how many of them do we have? 2 power k. How many possibilities are there for k minus 1 positions? 2 power k minus 1. Okay, so you have 2 power k vectors. So what should happen? There should be 2 rows where these 2 things repeat. Okay, at least one possible repetition has to happen. Okay, so maybe let us say the ith row and the jth row repeat. Okay, so in the ith row and the jth row, what will happen? What will happen in the jth row? I will once again have Ci1, Ci2, Ci k minus 1. Okay. So and here you will have all kinds of stuff. Okay, so I do not know what else is there. So what can I say from the ith row and the jth row? I am going to say with one more step you will get a relationship between d, n and k. If you add these two, what will happen? Last bit. The first k minus 1 bits will become 0. Or another way of looking at it, instead of adding another thing, if you look at the distance between the code word, the ith code word and the jth code word, what can possibly be the distance? N minus k minus 1, which is n minus k plus 1. Okay. So whenever I write down 2 power k code words, okay, there will be 2 such code words which can possibly differ only in the last n minus k plus 1 positions. So clearly the minimum distance cannot be greater than that. Okay, so minimum distance is less than or equal to n minus k plus 1. Okay, so this is what is known as the Singleton bound. Singleton is the name of the person who came up with this bound, I think. No other reason. Yeah, so there are other ways of proving this which use the generator matrix and parity check matrix. What could be one advantage of using this proof that I wrote down here?
If the d is n minus k plus 1, you know
that with the generator matrix also. So we have been always talking about linear codes. It is not necessary to restrict yourself to linear codes. You might want to have non-linear codes. Okay, so the proof I wrote down will work even for non-linear codes, even if the code is not linear, as long as it's just a simple combinatorial. This is called a pigeonhole principle in combinatorics. So it's just a simple argument, nothing beyond it. So if you use the generator matrix, parity check matrix, that proof holds only for the linear codes. Okay, so that's all. We won't see non-linear codes in this course, so don't worry about it. But nevertheless, this is a good proof to know. Okay. All right. So now let's see if you can give me examples of codes that meet the Singleton bound. Okay, so codes that meet the Singleton bound are called. Once again, let me remind you what the Singleton bound is. I have an nkd code. I know definitely d is less than or equal to n minus k plus 1. Okay, codes that meet the Singleton bound are called maximum distance separable. Or MDS. MDS codes meet Singleton bound. Okay, maximum distance separable is the name. Okay, so I want some examples. Okay, so repetition code clearly is an MDS code. Okay, see once I write n1n it becomes unique, right? It's only the repetition code. There's no other code that can work out. So n1n. Okay, and you will see the dual, the n minus 1 2 code will also be an MDS code. In fact, you can show this as a general property. If C is MDS, CPUB will also be MDS. Okay, so we won't see such proofs today, but anyway, it's a good thing. If you think you can prove it, you can try to prove it. It's an interesting proof anyway. Okay, so if code and its dual will both be MDS. So what's another interesting thing is there is no other binary MDS code. That's all. We listed out all the binary MDS codes. Okay, no other binary code is MDS. Okay, if you go to other finite fields, there are MDS codes. Of course, the celebrated Reed-Solomon code is an MDS code. Okay, so we will see that eventually, but in the binary field there are no other MDS codes. Okay, so for instance, the 743 Hamming code is kind of optimal in some way. There cannot be a 744 code. Okay, so that's possibly the minimum best distance that you can get. Okay, so that's I have not proved that to you. You can try a proof. Okay, I will encourage you to try to prove that statement. Okay, why is it that for binary codes you can never have any other code? So basically you have to show if k is greater than 2, greater than or equal to 2, immediately you cannot have MDS property. Okay, that's enough. The dual, like I said, will also be a MDS code. So n minus k will also work out. So it's not a problem. To show if k is greater than or equal to 2, then you cannot have MDS. That's the idea. Of course, I mean n minus 1 is possible, so you have to also limit it at n minus 2. Okay, so that's the idea. Okay, so that's Singleton bound. So the last 10 minutes we will see another bound which we won't use too much, but it's also very vital and interesting bound. It's called the Gilbert-Virchow bound. Okay. So the previous two bounds that we saw are inequalities which have to be satisfied by all codes. You start with an NKD code, they have to absolutely satisfy those inequalities. The Gilbert-Virchow bound is actually an existence result. Okay, so it's not a bound for all codes. Okay, there can be codes that violate this inequality that I am going to write down. Okay, but it is an existence result. Okay, what do I mean by existence result? Yeah, so if you have an n, k and d which satisfy this relationship, then there exists at least one code with those parameters. That is what it means. Okay, and there is another way of looking at it which makes this code really, this bound really very important, but we will not go too far into that. But basically it is an existence result. The way you prove that is a little bit interesting. I will write it down real quick. We do not have too much time and we won't spend too much time on this. The basic idea is to construct a parity check matrix with r rows column by column. Okay, so you keep constructing it column by column and you always maintain a minimum distance d. Okay, you want to keep maintaining a minimum distance d and you have r rows and you keep adding column by column. Suppose you have added n minus 1 columns. Okay, we have already added n minus 1 columns. Okay, it's kind of an inductive thing, but anyway, so let me just write it down real quick to get you the final answer. Okay, I will write down an equation or an inequality which will tell me that I can add a nth column also. When can I add the nth column is the question. Okay, I will write down an inequality. It is quite easy to write down, but if that is satisfied, it means I can add a nth column also, and then you keep iterating on this inequality, you will get this bound. Okay, so that is the idea. So let me write it down. Okay, so you have n minus 1 columns that I have already added. Okay, and when can I add the nth column is the question. Okay, see the nth column cannot be the all 0 vector, okay, it cannot be the all 0 vector, and it cannot be any one of the previous columns that I added, and it cannot be the sum of any two of the previous things that I added, so on I can go to, it cannot be the sum of any d minus 2 columns that I added. It can be the sum of d minus 1, because in that case I will have minimum distance d, that is not a problem. Okay. These are the total number of possibilities which are excluded for the nth column. I can never add any of these guys. Okay. In fact, I might be over counting here, but does not matter, I just want a bound, and this is good enough bound, so I do not care. Okay. So I am just adding it up. This has to be strictly less than 2 power r. If it is less than 2 power r, then I can definitely add the nth column. Okay. So this is the condition for the Gilbert-Vershamo bound. Okay. So it is a good bound, I am just giving you an argument for why that bound comes from, but it is very useful. Okay. So codes that meet or are better than the Gilbert-Vershamo bound are usually called good, say they are good. Okay. No other great word for them. So code is usually supposed to be good, well it is not really, that is not the only condition. Okay. The good is a vague word, but in general if you meet the Gilbert-Vershamo bound, it means you are doing something which is not very bad, it is a good thing. Okay. But of course there can be parameters which beat this bound and still there will be a code. Okay. So this is not a bound in that sense, just showing you an existence result. If there is, this condition is satisfied, you can have a bound, it is a good bound in this sense. Okay. Okay, so what we are going to do next is try a simple little example which will maybe bring together some of these bounds and give us some feel for what happens. Okay, so here is an example for designing, let us say a design for let us say d equal to 4, n equals 31. Okay. Suppose I tell you my block length I want is 31, and the minimum distance I want is 4, or let us say greater than or equal to 4. Okay. So if I say greater than or equal to 4, you might want to just pick 4. Okay. So I want to maximize k. Okay. What is the largest possible k that I can have, which will give me for n equals 31 a minimum distance of 4. You can say greater than or equal to 4 for d, but then you would pick d equals 4, right. I mean, if you want to maximize k, you want to pick the smallest possible d, because you know if k goes up, d will go down. Okay. So that is how it will work. Okay. So it is a good picture to keep in mind, is that sphere packing picture that I drew. If k keeps on increasing, the number of stars is increasing, and you should be able to only draw a smaller sphere. Okay. So that is the simple picture you can keep in your head to convince yourself why this tension is there between k and d for a fixed n. Okay. Alright, so take a crack at it, it is an interesting problem. Okay. What is the maximum possible k that you can come up with based on the knowledge that you have? Do not blindly apply the bounds. Okay. I want an actual parity check matrix. Okay. The bound will not give you a parity check matrix. Okay. So one bound, if you use the Singleton bound like he is using, k has to be less than or equal to n minus d plus 1, which works out to 28. You will not get anywhere close to 28, believe me, because you know already that I told you an informal result, not an informal result, it is a very valid result, but I told you informally that no binary code will meet the Singleton bound. Okay. So you will not get there, and you do not have too many perfect codes either, so even the Hamming bound will be violated a little bit. Okay. So you have to construct a parity check matrix, you have to construct an actual parity check matrix which will give me k. Yeah, so you have to do extension. The question is how many rows will you have for the parity check matrix, right? You have to minimize the number of rows for the parity check matrix, am I right? Okay, so suppose if you want to construct a parity check matrix H, okay, you want to minimize the number of rows. Why do I want to minimize the number of rows? Yeah, so n is fixed at 31, I want to maximize k, which means I have to minimize the number of rows. Okay, so I want to minimize number of rows, but I still want to have a minimum distance of 4. Okay, so remember how are we going to construct minimum distance 4? We are going to start with minimum distance 3 and then extend. So in extending I will go from n to n plus 1, right. So after extending I want 31. So before extending, what should be my code length? 30. Okay, so I have to now think of just the first 30 columns and put down some rows, and then finally I will add one row for the extension. Okay, so what is the minimum number of rows I should have for a length 30 code with minimum distance 3? That is the question. 5, right? You have to have 5. 4 is not enough. Why is 4 not enough? Yeah, because 2 power 4 is only 16. Clearly you are going to repeat something. Okay, you cannot repeat. So if you should not be repeating, you need at least 5 rows. Okay, is that okay? For this you need 5 rows. Okay, so for the 30 you need 5 rows. Okay, so this guy will be 5 cross 30. Okay, will have distance 3. It will be equal to 3, right. That also you can be reasonably sure, you cannot be greater than 3, it will be equal to 3. Okay, because you are picking out 30, it will come out to be 3, and then you extend 1. Okay, and then you put all 1s here and then put all 0s here. The overall guy will have a distance equal to 4. And what is k now? Okay, so I have to be sure that these 5 rows that I put down will give me a rank 5. You can be sure that will also be true. Okay, so you are putting so many vectors, you can surely find 5 columns which are full rank. Okay, so you can think about it, convince yourself that that's true. Okay, so it's not too difficult to show that. So rank will be 5. So clearly k works out to 31 minus 6, which is 25. Okay, so we have a 31 comma 25 comma 4 code. Okay, now the question is, how good is this code? Can I possibly have gotten 26? Can I have gotten 27? I don't know, right? Okay, so we don't know these things very well. In fact, there are people who maintain extensive tables of best possible codes. So you can go to one of these tables. There is a table maintained by N.J.A. Sloan, who works in AT&T Bell Labs. He is a very famous coding theorist. You can search for him. He maintains a lot of tables. One of the tables he maintains is for the best possible code. Okay, so you can go look it up in that table. Okay, so you will know. Another thing to do is to plug in the bounds and see how close you are to the meeting the Hamming bound and the Gilbert-Ostromov bound. If you are close enough, then you can be reasonably sure that you are okay. Okay, so plug these values into the, let us say, the Hamming bound and tell me what k you get there. Okay, 26 for the Hamming bound. Okay, what about Gilbert-Ostromov bound? Okay, so there was a claim here which says Hamming bound tells you k is less than or equal to 26. Okay, which already means you are doing a reasonably good job, you are not too off the charts. Then the Gilbert-Ostromov bound, if it gives you k equals 26 for instance, then it means you are not the best possible. Okay, clearly, but if it gives you anything else, you can't be sure, right? That's the problem. Okay, so you can check those things. Alright, you don't have to do it now, you can do it later, but plug in these values of n and d in those bounds and find a bound for k. Compare with what you've got and see if you're doing okay or not. Okay, so once again, remember the interpretation for Gilbert-Ostromov is different. If you get a larger k, what does it mean in Gilbert-Ostromov? It means, if you get, for instance, in Gilbert-Ostromov k equals 26 is possible, then it means, yeah, you can get something that's strictly better. Okay, but if you get, for instance, k equals 25 in Gilbert-Ostromov, then you can't be sure. I mean, 25 is possible, it says 25 is possible, maybe 26 is also possible, you cannot rule it out. Okay, that's the problem. Okay, that's right. Okay, so we'll stop here.